From dust we come, to dust we return. In many different cultures, this statement is used to poetically describe the birth and death of human beings and the modesty of our existence on earth. But today, I'm going to expand the scope of this statement and talk about the universe instead. From stardust we come, to stardust we return. What does we refer to? It still includes us, but also all of the planets and stars. In the universe, dust has existed for billions of years. Surprisingly, these dust grains are tiny, but they play a disproportionately important role in the evolution of the universe. They drive a much larger cycle of birth and death of stars at the cosmic level. Dust is not merely responsible for creating us. The sun and the earth exist because of dust. But what is dust? The word dust is used to describe a wide range of solid particles. It can be the layer of dirt on your bookshelf, snow that falls in Montreal, sand in the Sahara Desert, clouds in planetary atmospheres. In the universe, dust is made up of a bunch of condensed out molecules. These dust grains are really tiny, smaller than 1/100th the size of a human hair. But we can detect their presence all the way from the earliest galaxies to our own stellar neighborhood. We are made of dust. The earth is made out of dust. But what is dust made up of? To answer this question, we do a bit of detective work. Dust absorbs light. The color of the light that it absorbs tells us what the dust is made up of. So we use telescopes to look at stars and see what light gets absorbed by the dust between the stars and us. What we have learned from such exercises over the last few decades is this. Elements such as silicon, iron, magnesium, the very things that make up the earth, are contained entirely in dust. In addition, there is a lot of carbon in cosmic dust, and all life on earth is carbon-based. So we come from dust, but where does dust come from? The early universe was very hot, and it only contained hydrogen, helium, and a bit of lithium. So the universe was not born with the elements that make up dust. We suspect that the earliest stars were made of only hydrogen and helium, and through nuclear fusion, they created elements that eventually formed dust. And when these stars ended their lives in massive explosions called supernovae, they scattered these elements back into space, eventually forming the dust we see today. The power of the explosion itself can create new and rare elements that also form dust. We now have evidence of supernovae creating lots of dust from observations of such events in the Milky Way and other galaxies. These images here, taken with the James Webb Space Telescope, show two supernovae in a nearby galaxy. These explosions created huge amounts of dust, equivalent to thousands of times the mass of the Earth. The elements that make up dust are therefore created by stars and released back into space when stars die. The dust that is created by these exploding stars helps create stars like our sun. The sun wouldn't exist if the universe were devoid of dust. This is because stars form due to the collapse of gas clouds. If the gas is too hot, you can only form stars that are very massive, like the ones in the early universe. It is dust that helps cool down the gas because it is really good at absorbing energetic light that would otherwise keep the gas too hot. It releases this absorbed energy as infrared light. Infrared light is redder than the reddest light we can see, and it has lower energy than visible light. This helps keep the gas cool enough to form stars like our sun. These images here show a star-forming cloud in visible light and in infrared light. You can see how dust blocks all of the light in the visible, but not in the infrared. The temperature of this cloud is measured to be a mere 16 Kelvin, or minus 257 degrees Celsius, and it is on the cusp of forming a star. This cloud would not be so cold if not for the dust. The cyclical nature of dust's role is therefore apparent. Dust came from stars, and now it helps create stars. Not only does dust enable the formation of stars like the sun, it also enables crucial interstellar chemistry that produces many key molecules. Dust acts like a catalyst in these celestial chemical reactions. The hydrogen molecule, which is the most common molecule in the universe, is produced by two hydrogen atoms coming together on dust-grained surfaces. Similarly, water, the molecule that is considered essential for life, is also formed by oxygen and hydrogen atoms coming together on dust grains. In extremely cold environments, all of the molecules such as water, carbon monoxide, and nitrogen condense out as icy materials on dust grains. The surface chemistry that happens next produces complex organic molecules, which are the ingredients of life. We finally come to a role of dust that is perhaps the closest to my heart, and certainly one that affects us most directly, and that is the formation of planets. When stars form from collapsing gas clouds, they end up with a spinning disk of dust and gas around them in which planets form. Over time, tiny dust grains that are smaller than the width of a hair turn into planets that are thousands of kilometers in size. You can imagine that this must be a complicated process. The smallest dust grains in these disks stick together to form millimeter-sized particles. This image is of millimeter-sized dust in a disk in which planets must be forming. Many of these disks are not smooth, but have these rings and gaps that you see here. These millimeter-sized particles clump together due to gravity and form planetesimals. Planetesimals are like little Lego bricks that come together to form planets. Here you can see an example of two planetesimals that are about 10 to 20 kilometers across, stuck to each other in the outer solar system. The gas disks that planets form in only stick around for a short amount of time in an astrophysical context, roughly 10 million years. Most of the dust in these disks ends up within the stars and the planets orbiting them. But some dust continues to exist in the form of planetesimal-like bodies, such as comets and asteroids. Meteorites are samples of such small bodies that fall onto the Earth. Their physical and chemical properties tell us about the conditions in which planets formed. In the bottom right, you can see an image of one of the most famous meteorites, the Allende meteorite. It is rich in carbon and has many small centimeter-sized spherical particles like the ones you see here. Such meteorites have barely changed since the sun formed, so they're like time capsules. They provide us with one of the most pristine records of the early solar system. Comets are like messengers from distant parts of the solar system. They tell us about the icy materials that exist far away from the sun. Comets are often very dim and hard for us to see unless they come close to the sun. Near the sun, they start losing their icy materials, which forms a tail, which is much larger than the comet itself, thus making the comet visible. This image is of Comet 67P, taken with the ESA Rosetta mission, which rendezvoused with this comet, and even landed a man-made probe on a comet for the first time. Small bodies such as asteroids and comets might be responsible for delivering water to the Earth, which is essential for life as we know it. Together, these objects allow us to piece together the history and building blocks of planet formation. Most of the dust that gets incorporated into stars eventually returns back to space. Stars burn their hydrogen and helium into heavier elements such as carbon, oxygen, and iron via nuclear fusion over billions of years. When they run out of fuel to do so, they start to die. At this point, they return a lot of their mass back to the universe via violent explosions or gentle outflows that form the kind of planetary nebula that you see here. These processes return dust back to the galaxy. To stardust we return. This dust will eventually end up enabling the formation of new stars. What happens to the planets and the small bodies that are orbiting the star when it dies? Well, some of them get engulfed by the star as it expands into a huge fiery ball of plasma. But planets that are far away from the star continue orbiting it even after it dies and becomes a white dwarf. Sometimes, asteroids venture too close to these white dwarfs, get ripped apart by their immense gravity, and fall onto the white dwarfs. We see evidence of this in the atmospheres of at least 25% of such white dwarfs. Imagine the journey that these dust grains have been on to end up here. Let me return to what I started with. From stardust we come, to stardust we return. Compared to the universe, we are indeed just dust specks. But I do not want you to think about this quote only from an anthropomorphic lens. We are not just talking about humans here. At the universe's level, this quote takes on a much larger meaning. It shows how seemingly insignificant dust particles play an essential role in all the important events in the universe. Dust is central to the cycle of birth and death of stars. It enables the formation of some of the most important molecules in the universe. And most consequently for us, it comes together to form planets, one of which we live on. Thank you.